Hello and welcome. Today we're going to be showing you all the basics that you need to know to get started in GAUSS with time series data. We will cover all the fundamentals: importing time series data, exploring and cleaning data, time series plots, preparing time series data for estimation, and estimating a basic time series model. Let's get started by loading some time series datasets. First, we will set our working directory to the location of our data. Notice that the current working directory shows up in our Project Folders window. The Project Folders window is a useful GAUSS tool. It allows us to access all the files that are in our current working directory, as well as any custom project folders that we have added. Let's double-click on the Federal Funds CSV file to open it in the Data Import window. This file contains historical quarterly data for the U.S. federal funds rate, which we have downloaded from the FRED database. In our data preview window, we can see that this dataset contains two variables, a date variable and our observed data. Our dates are stored in a standard format, and GAUSS automatically recognizes the date variable and loads it as a date type. GAUSS recognizes most common date formats. If you need to import a date with a non-standard format, check out the resources in the description below. Our observed variable isn't named very intuitively, so let's rename it. Note that as we make our changes, the code preview box is being updated. Everything else looks good with this data, so we're ready to import it. When we click Import, GAUSS will load the data and take us to the data page. Let's double-click the name of our new data frame in the Symbols window so we can take a look at it. Now, let's load our second data set from the unrate Excel file. This file contains monthly unemployment data from the FRED database. This data is less friendly for loading than our federal funds data file was. It contains an extra header which we don't want to load into GAUSS. To remedy this, we will use the import options to specify row 11 as our header row. When we update the header row, notice that our preview window updates to indicate that rows 1 through 11 will not be imported. If we switch back to the Variables tab, we can also see that our variable names have been updated based on the new header row. Finally, we will update the date column variable to date and import our data. After loading our second data file, we see that our original data frame is still available. GAUSS allows you to have as many data frames loaded at a time as your computer can handle. One of the great things about the GAUSS data import tool is that it outputs the code that we need to reproduce these steps in the future. It's always good practice to save your analysis steps in a program file for verification and reproducibility. Now let's go back to the edit page where we can find the auto-generated code and create a program file for our analysis. Notice that the code created in the import window uses the full path or the absolute path to load the file. If you don't include the path, load D will look for the file in your current working directory. Formula strings are a convenient way to specify which variables you want to load, as well as their types or any transformations that you'd like to make. The date keyword tells GAUSS that the first variable in both our FFR and unrate files is a date. You can open the help for load D or any function by right-clicking and selecting Help on selected text. More details on formula strings can be found in the description below. As is often the case, our data came from different sources, but we would like to merge them into a single data frame. We can merge our data on the date variable using the outer join procedure. Most of the time, you will want to use the full option with outer join. It keeps all observations from all variables that are being merged. Outer join does not sort the data, so we'll add a line to do that as well. Now we'll run the file. After merging our data, we can conveniently view our new data frame from within our program by placing our cursor on the symbol name and using the Control-E or Command-E on Mac hotkey. Our data has merged correctly, but still needs some further cleaning. Our raw data has different date spans, so let's filter the data to remove all observations before January of 1960 and after October of 2021. We can do this using the Data Management tool. After setting up the filtering conditions, we need to apply our changes. Today we will overwrite the existing data. However, the dropdown also has an option to create a new data frame if we want to keep our original data. The Data Management tool generates the code for our filtering, which we will then copy and paste into our program file. Now that we've filtered our data, we're ready to look at summary statistics. Our summary statistics look as we expect. The date ranges from January 1960 to October of 2021. There are no missing values of our monthly data, unrate, and there are 494 missing values of our quarterly data, FFR. Let's remove these missing values. Pack R stands for pack rows and removes all observations that contain a missing value. We'll use the up arrow key in the command window to find our dstatmt call and run it again. Great, no missing values this time. This leaves us with a quarterly dataset that uses beginning of period observations of unrate. Finally, we will confirm that our data does not contain duplicate observations by using the isUnique function. IsUnique returns a 1, confirming that we have no duplicate observations in our dataset. The next step for our analysis is to look at our data using time series plots. We can get a quick time series plot of our data using plot xy in a formula string. After running the plot xy procedure, we are taken to the graphics page. Notice that when we plot using formula strings, the y-axis is automatically labeled, the legend is automatically generated, and the lines are drawn in default Gauss colors. While these are good defaults, let's use the Graph Settings tool to modify the graph. We can open the graph editor through the View menu and by selecting a plot. The first window we see controls the size of the entire graph canvas or figure. Let's make it a little bit wider. Next, we'll click on the graph to bring up the other graph attributes in the graphics editor. The Graph Settings tool groups graph features together based on type. For example, all settings related to the graph title are found in the title group. Let's use the title settings to add a title to our graph. First, we will double-click on the caption option to open a text box. Our title is added to the graph, but it's a little bit too small. Let's use the Title Font Settings dialog to change the size of our title to 18. The Graph Settings tool is a great way to interactively modify a single graph, but it isn't always convenient if we have multiple graphs that we'd like to customize. All graphics options can be set programmatically, which allows them to be easily replicated in the future. Now that we have loaded, cleaned, and explored our data, it's time to perform stationarity testing. We'll use the TSPD library for this. It's available for free and provides extensive tools for time series and panel data stationarity, co-integration, and causality testing. Before getting started, there are a few helpful steps that we can take to make sure our workspace is ready. First, let's confirm that the tspdlib library is installed. We can see that tspdlib has been installed and is included in our library list. For more help installing libraries, see resources in the description below. Next, we will add the Gauss Packages directory, Packages, to our project folders. This will allow us to quickly locate the example files we will be working with. Now, we're ready to open an example file for our unit root test from the tspdlib library. Today we will run the ADF test with one structural break, which can be found in the ADF under onebreak.e file. The example file uses data included in the library and runs 4 different versions of the test. Since the plot of our data didn't indicate a time trend in the unemployment data, we will only run the model with a break in the level. For convenience, we will also just run the test with innovative outliers, which is the default setting. Let's view our program file and the ADF under one-break example file and copy the code for assigning our testing variable y and for running the test and paste it into our analysis file. Now, let's modify the code to test our unrate variable. The dot index tells GAUSS that we want to use all rows in the data frame and the variable names date and unrate specify to copy those variables to y. The date variable does not have to be included in y to run the test. However, when it is included, tspdlib will specify breakpoints in the same format as our dates. We also need to load the library before we can use the tests in tspdlib. Finally, we're ready to run our test. When we run our file, GAUSS prints a results report. The results report contains a summary of the test that was run, including the null hypothesis, the computed statistics and breakpoint, and the conclusion of our test relative to the null hypothesis. We can see that in this case, we cannot reject the null hypothesis of a unit root and that the single break is estimated at the first quarter of 1970. We will finish our analysis today by performing an ARIMA estimation on our unemployment variable. To do this, we will be using the time series MT application module. This module is sold through the AppTech website. Let's add TSMT to our list of libraries to load. Now, we will search our project folders for a related example file to help us. Let's use the ARIMA fit example, arimafit1.e. Let's copy and paste the ARIMA fit model setup so we can modify it to estimate an AR2 model using the first differences of the unemployment rate. We'll copy the last 3 lines of actual code. Line 44 tells GAUSS that AMO is going to be an ARIMA MT out structure. Structures hold many different pieces of data in one tidy package. As we'll see shortly, the ARIMA fit function will fill out the data inside the structure. If you are unfamiliar with structures, don't worry, we'll show you how to easily view and access the data that they hold. First, set y to be our unrate data. Then, change p equals to 2 to indicate that we will be running an AR2 model. Finally, we need to add an additional input d to our call to indicate that we want to run the model in first differences. The ARIMA fit procedure prints a full output report to our screen, including diagnostic statistics for model selection, such as the log likelihood, the AIC, and the SBC, the AR2 coefficients and their standard errors, t-rations, and p-values, and the AR2 roots for checking stationarity. Now that we have seen the printout, let's see how we can look at the data from the estimation. We'll go back to the data page. Under the list of data frames, we see the structures. In this case, we only have one, which is the ARIMA MT out structure that holds the estimation results. Expanding the node next to AMO lets us see all of the data being stored in the structure. We can double-click on any node to examine a particular member. Let's open the parameter estimates in B. It contains both AR parameter estimates, and the third estimate is for the constant term. We'll also open LL, which contains the log likelihood value, and finally E, which contains the residuals. If we look up at the tabs that we just opened, we can see that they are named AMO dot and then the member name. The dot operator is how you reference data in a structure. Structure instance dot structure member. For example, AMO.B. It's pretty simple, isn't it? In this video, we loaded time series data from CSV and Excel files, explored, cleaned, and merged the data, created a time series plot, performed a stationarity test, and estimated a basic ARIMA model. I'll see you guys next time. Leave any questions or comments below. Thanks for watching.